Okay, thanks for joining me for this webinar. This is an encore presentation of one we did a couple weeks ago. We know that not everybody is able to attend at a given time, so we wanted to offer this twice to give other people a chance in case they missed it the first time. I am Eric Bjornstad. I'm the Technical Information Director here with Bell Performance, and the topic we're going to be discussing today is recent fuel changes and how those fuel changes affect you. And specifically what we're going to be looking at is we're going to be looking at some of the key ways that fuels have changed. We're going to be talking about specifically about gas and diesel. We're going to be talking about how and why those changes came about. We're going to talk about the consequences and the problems arising from those changes, and what those look like in practice where you are at. And then finally, we're going to be talking about some of the best practices within the industry to address those problems that people are coming up against. So basically, there was a Greek philosopher about 2,500 years ago, Heraclitus, that said that the one thing that doesn't change is that things change. And that's certainly true of the gas and the diesel fuels that we use today. Gas and diesel have changed markedly throughout the years. And they have changed in response to the needs of the consumer and also the needs of the equipment that use those. Engines are completely different than they were in the late 19th, first half of the 20th century. Now you've got common rail diesel engines, you've got gas engines with much higher compression ratios, and they've had to change the fuels in order to keep up with those and in order for those to meet the needs of the consumers. So technology's changed, fuels have changed, the world itself has changed markedly, and that's one thing that we're going to talk about in order to try and give some context into all of this. And specifically, we're going to start by looking at the issue of energy in the world and the supply and the demand and how that has changed from years past. The biggest change, back, let's see, probably about 10 years ago, there was a book written by Thomas Friedman called The World is Flat. It was a very interesting book, and the main thesis of the book was that the world is changing markedly. People are a lot more connected, and the world's actually getting smaller because of the way we're able to connect with other people in ways we were never able to before. But one of the big things he talks about is the fact that the developing world is growing and consuming resources at a much faster rate than they used to. Now, an example of this is just look at internet usage. Here in the United States and in Europe, we're used to thinking of the internet as our domain. We're the ones that use it. The third world doesn't tend to use it. That's what we think. But in the United States, we have about 270 million people that use the internet out of a population of 350 million. China has 650 million internet users. India has 352 million internet users. That's more people than in the entire United States. Yet we don't think of those developing countries as people who use that to any great extent, but they do. Now, look specifically at energy. We asked the question, who's using the energy? Well, in 2012, the International Energy Agency reported that for the first time in recorded history, oil consumption in developing countries actually surpassed developed countries. It was the first time in history that ever happened. If you go back to the year 2000, start of the 21st century, developing world was using 70% of the energy. Now their demand has surpassed what the developed world is using. The developing countries we're talking about are China and India, but also countries in Southeast Asia, countries that used to be considered third world, and by and large probably still are, but they have a growing population that is basically reaching out and trying to grab their share of the world's resources. And so when you have this demand that is growing and growing and growing, sometimes the ability to supply that demand struggles to keep up. And when we're talking about things like energy, crude oil, and fuel, in that respect, what we're talking about is refining capacity, the ability to take crude oil and turn it into the things that people tend to use, gas and diesel. The refining capacity of the world has struggled to keep up with the demand. Now, look at the United States. Go back to 1982, the United States had about 300 refineries that had the capacity to refine 17 million barrels of oil per day. Fast forward about 30 years, 2013, the United States has 139 refineries, less than half. But they still have the same capacity, 17 million barrels a day. So you've got half the refineries refining the same amount of fuel, which means they're twice as efficient doing it, but they're under twice as much pressure to keep producing that, because if they stop, then there's going to be problems. You know, we've all seen what happened when a storm hits the southeast and knocks out a refinery in Louisiana. Gas prices shoot up because all of the refineries are working at a breakneck pace just to keep up with the demand. So demand is something that we're going to come back to a little bit later and talk about a little more, because it's definitely one of the drivers for this issue of how fuel has changed. Another key driver is the environmental movement. You know, whether you want to call it green consciousness, whether you want to call it, for being a friend of Mother Earth, whatever you want to call it. There's more and more people now that are concerned about the environment than ever before. And so when the populace is concerned, Congress and the government tend to get involved. They tend to, or rather, they are more likely to take action if the people are more concerned about it. And so what you've got increased green consciousness has led to more congressional action, and that congressional action is what has impacted the fuels that we use today. One of the things we're going to mention again later is the Clean Air Act of 1990/1992. That is a key event that changed the fuels that we use and caused some of the changes that we're going to talk about and what has brought us to our current situation. So what we're going to do now is we're going to talk about some of the big changes that have happened in the fuels. We're going to talk about why those happened. We're going to talk about how those specifically changed specific things in the fuel that have caused specific problems that you might be seeing now. So we're going to be doing a lot of contrast between looking at what fuels used to look like before 20, 30, 40 years ago and what they look like now. Okay, first thing that we talk about is we're going to talk about this thing called cracked fuels, or fuels that are made with cracked feedstocks. Okay, the first big change is that the storage life of fuel is completely different now than what it used to be. Back 20, 30, 40 years ago, the storage life of fuel was much longer. There was a study that was commissioned by the U.S. Army in the 1960s. They wanted to study fuel storage life. And what they found is very interesting. They found that the expected storage life of gasoline, just regular gasoline, should be 2 to 5 years without any problems. Expected storage life of regular on-road diesel fuel should be up to 10 years or more. That's what they found in the 1960s. So the old storage life, 2 to 5 years or more. What is the storage life like now? Well, not even close to what it used to be 20, 30 years ago. Now, storage life of gasoline, if it has any ethanol content, which virtually all on-road gasoline does, expected shelf life for that is 90 days. For diesel fuel, number 2 on-road diesel fuel, you put it into storage in 1 month, you can expect the storage quality of it to degrade about 25%. And that can be anywhere up to 70, 80, 90% if you've got things like water or microbes in that fuel. So big difference is storage life of fuel is way down compared to what it used to be. What changed? That's the question. Why, what changed about it? Well, in order to answer that question, we have to cycle back to the supply and the demand issue. Demand is at an all-time high. The ability to fill that demand has been struggling to keep up, and so you've got greater and greater pressure for the refining industry to get more gas and more diesel out of crude oil. You can see this illustration here. A barrel of crude oil, which is 42 gallons, they tend to get a certain amount of the main components out of it. You see they take gas, they take diesel, jet fuel, they have heavy fuel oil, which is the residuals, the natural gas, and then the asphaltenes and the tars that are left over. Now, what they want to do is, in order to meet this demand, they want to get as much gas and as much diesel out of that crude as possible. But there are limitations to what they're able to do. Right now, they're up to about 29 gallons out of every 42 gallons of crude oil becomes gasoline and diesel fuel. They would like it to be more than that. And so what they have been able to do out of necessity, really, is petroleum chemists have developed what they call hydrocracking processes that they can use at the refinery to get even more gas and even more diesel out of that crude oil. Now, in order to understand this better, you have to understand basically what we're talking about when we talk about cracking. You know, what is it all about and what do we mean by it? Well, consider that crude oil, when it comes out of the ground, it's a natural blend of a variety of large and small size molecules. And those molecules are typically defined by the number of carbons that they have in them. Different sized molecules tend to be associated with different components. Gas and diesel fuels are made up of molecules that are between 8 and 21 carbons long. But there's a sizable part of the crude oil that it's even bigger than that. You can have molecules that are hundreds of carbons in size. So what the petroleum industry did was they developed a cracking process to crack those molecules, break them apart, and turn them from large molecules into smaller ones. And they were able to target this to get more molecules of the size that make up gas and diesel, and therefore you get more gas and diesel out of it. And that's great. You know, that solves the problem to a certain extent, but it doesn't mean that there aren't consequences that happen when you do this. And the main consequence is that if you have a fuel that has a certain amount of what they call cracked feedstock, because they will blend that in, they'll use that as a filler. The more cracked feedstock a fuel has in it, the more likely it is to react and to degrade and to lose stability over a given period of time. And the reason why is because when you take a long molecule, like in this illustration, you take a long molecule and you do something, you break it apart into two smaller molecules, what you tend to get is those smaller molecules tend to have double bonds in them. They're what they call alkenes, if you're a chemist. And double bonds tend to be more reactive. They're less stable and they're more reactive than single bonds are. What that means in practice is that those molecules, those cracked molecules, now are in the fuel, and they're going to go around, they're going to try to react with other molecules, and they're going to start catalyzing reactions in that fuel that are going to eventually cause it to become unstable and break apart at a faster rate than if they weren't there. So the consequences of this for where you're at in the real world is, as we said, poor storage life. Cracked fuels lead the refinery with greater numbers of unstable molecules, and these molecules are reacting, and when they react, they don't just react without consequences. What happens is that they tend to join and they tend to form longer and longer and bigger molecules as they react. And so what you start getting is you get formation of longer and longer polymers in the fuel, and eventually, you give it enough time, eventually these molecules become big enough that they are too big to stay dissolved in the fuel. They start to drop out of solution. And when that happens, you get color change in the fuel. The fuel starts to darken. Things like sludge and varnish and gums start to form, and those are the things that are going to be causing some of the problems that we're going to talk about. What does this look like in the field? Okay. What that question means is, if you are a fuel user, where you at, what problems is this going to cause for you where you are at? Well, to a certain extent, the problems are universal, but the how you use the fuel, basically, whether you are a fleet user, for transportation, or whether you use it in emergency backup generation, that is going to influence the problems that are going to most impact you where you're at. So what does this look like in the field? Cracked fuel instability. Well, if you are a fleet operator or you're a driver, then what you're going to get is you're going to get things like the fuel's not going to burn as completely or burn as well as it would if it was fresh, and so that's going to lower the MPGs that you're going to get out of it. It's not going to burn as completely, which means you're going to get more soot and more smoke production from that. You're going to get injector deposits, and you're also going to get shortened life and shorter service intervals for your DPF, your diesel particulate filter system. All of these happen because the unstable fuel, because of the cracked molecules in it, the unstable fuel is breaking apart. It's not burning cleanly. It's not burning completely in the engine. You're not getting the full energy value out of them. You're getting all of these problems. The big one to be concerned about if you're a fleet or a driver is the injector deposit issue. Injector deposits happen because you're running fuel through them that already has sludge or gum or heavy polymer components already dropping out of it. Those are going to collect in that injector. They're going to cook. They're going to react with the heat and the pressure that's already inherent in an injector tip, and you're going to get deposits formed in that injector tip. And the problem that causes for the trucks is that it affects the way the fuel atomizes. You don't get the best, most efficient functioning of that fuel injection system, and injector deposits are the single biggest influencer for mileage for any fuel-injected vehicle, apart from, of course, driver behavior. So those are the ways that cracked fuel affects fleets and drivers. On the other side of the coin, you've got people who tend to just basically they store the fuel and they use it for generators and for emergencies. Those people are going to have similar problems, again, because it's reacting in the same way for them as it is for the fleet and the truck driver. They're going to get sludge formation in the tank because that fuel is sitting there. All those heavy polymers that are forming, until that fuel is used, they're just going to be sitting there. It's just going to drop out. It's going to collect in the bottom of the tank. And the reason this is a problem is because, first of all, sludge, those molecules used to be part of the fuel. They used to be dissolved, soluble in the fuel. Now they're not, and that means part of the energy value that those would have contributed, it's not being contributed to anymore. So the amount of work they're getting out of it, we would say MPGs, but it's basically the amount of work that it can do is not going to be as much as it was before. The system is not going to be as efficient because it's lost energy value. And that sludge will plug filters, and if it does happen to get drawn into an engine to be used, well, it's going to cause the same kind of deposits that it's going to cause in diesel truck engines. Second thing, black smoke, as you can see from the illustration, that is a backup generator that is being load tested. All those black smoke and soot particles are particles of partially burned fuel. They're partially burned because large polymer molecules do not, diesel engines are not designed to burn huge, large polymer molecules. They're designed to burn molecules that are, 10, 15, 20 carbons in length, not 250. So all that is partially burned fuel. Unreliable system operation. That's a big one for emergency systems, for standby generators, for critical use systems, and we're going to touch on that a couple times more later. But that is a big one. They store the fuel in order for it to do a job, but if the fuel is not, if the fuel is unreliable, it's unstable, it's not going to burn as well, and that means you've got a greater chance of that system not running like you need it to when you need it to. So the bottom line for all this talk about cracked fuels. Greater demand means there's more pressure on getting more gas and diesel out of a finite amount of oil, and that means the fuels that they are producing are they burn dirtier, they burn less completely, and they do not store anywhere near as well as they used to. So that's the first big change. Greater use of cracked fuel or cracked feedstocks in gas and diesel. The second big one is something that everyone is probably well familiar with by now: ultra-low sulfur diesel, or the marked reduction in sulfur content that diesel fuel today has over how it used to be 15, 20 years ago. Sulfur is a natural component of oil because crude oil is a natural, it's a natural product. And so when you refine that oil, that sulfur ends up in the different components that you take out of it. So all fuels, except for the really light ones like the natural gas, all of the distillate and the residual fuels have some kind of sulfur content in them. Now, for most of the 20th century, regular, on-road number 2 diesel had a sulfur content of 5,000 parts per million. But around 1990, Congress decided that it was time to start looking at some laws to impact some of the environmental concerns that the public was concerned about. The depletion of the ozone layer, toxic, urban air pollution and smog, and acid rain was a big one. The pictures of those forests with all the dead trees. The public wanted, something done about that. And so what Congress did was they said, well, sulfur content, sulfur emissions from things like diesel fuel are the primary driver of acid rain. So what they did is they cut the amount of sulfur you were allowed to have in diesel fuel. And this was done at the refinery level. I'll be back in one moment. Hold on. Okay, sorry about that. I was informed that my sound had cut out, which is unfortunate. So what I'm going to do is I'm going to back up a moment, and I'm going to go back up to the top of this slide. Okay, so basically what we were saying was that because of congressional action, the sulfur content has been cut in diesel fuel. And what we've ended up with now is that instead of diesel fuel from before the 90s, which had 5,000 parts per million in it of sulfur, the diesel fuel now has 15 parts per million. That's a 99.7% reduction. Did that accomplish the goal of what they needed it to do? Well, I mean, if you're reducing sulfur by 99%, you're definitely going to have a very prominent positive effect on the environment. How do they remove the sulfur? Well, it's done at the refinery level, and they use what they call hydrodesulfurization processes. They basically take it out as H2S gas. They use that sulfur to make things like sulfuric acid, and what they end up with is a diesel fuel that has between 4 and 7 parts per million of sulfur, and that gives them a little bit of wiggle room for in case somebody adds something down the line that raises the sulfur content. Now, what effect did this have on the fuel itself? Okay, there's, I think, about 5 main effects that we're going to talk about. The first effect is the effect on the fuel lubrication, what they call the lubricity value of the fuel. Okay, generally, sulfur content in fuel has been associated with the ability of that fuel to lubricate things like injectors and fuel pumps. Injectors and fuel pumps have relied on the fuel lubricity value in order to lubricate them and make them, not wear out prematurely. Now, when you remove sulfur, then you lower the fuel's ability to do this. And so what this does for the user is it increases wear on these parts, increases wear on fuel injectors, on fuel pumps, and specifically, premature wear on parts, shortened part life, and of course, it stands to reason that you're going to get higher maintenance costs as part of that. So first problem, reduced fuel lubrication because they took the sulfur out. Consequence of that, increased maintenance costs and wearing out of injectors, things like that. Second main problem is lower energy content. Okay. When they process the fuel, they not only remove the sulfur, but they also remove other things like aromatics, which are a type of molecule that make up a significant portion of the diesel fuel. They remove those. What that does is that changes the energy value of the fuel, lowers the energy value, and anytime you have lower energy value, which is it's about a 1% reduction, anytime you have a lower energy value, then that lowers the MPGs for the consumer, for the user, and it also basically makes it more expensive. So how much more expensive? Well, 1% energy reduction or reduction in energy value doesn't sound like a whole lot. And when they were running the numbers, they were estimating that for every 100,000 miles that you drive, your costs are going to go up about $500. Now, for the average, for the consumer that has a diesel pickup truck, that's pocket change. They can find that change in their sofa. But for a fleet that has hundreds of vehicles running on diesel, that cost adds up, and that is an extra cost that could be used in another area. So it's significant for them. Also, a factor that plays into the cost of ultra-low sulfur is that it's more expensive to produce. They estimated that it was going to add between 5 and 25 cents per gallon to that diesel fuel. So you're getting a little bit less mileage, but it's also a built-in cost on the front end that is costing users more. So second effect of ultra-low sulfur diesel, it's more expensive, basically. Third effect, contamination or possible contamination with high sulfur diesel fuel. If you think about it, think about all the storage tanks around the country. A lot of their storage tanks are older ones that used to have high sulfur and low sulfur diesel in them. Now, when they started transitioning over to ultra-low sulfur diesel, some of those might have been drained and filled with ultra-low sulfur diesel. If you were to go and test all of those tanks, then what you would likely find is that a significant number of them have sulfur content that is too high, that's out of compliance. And the reason this is because it does not take very much leftover high sulfur fuel in the bottom of that tank to bring the whole mix out of compliance. And it's to a certain extent it's a mathematical issue. Let's say you have 1,000-gallon tank, and that 1,000-gallon tank used to have used to be filled with low sulfur diesel, 500 part per million diesel. But they wanted to switch it over to ultra-low sulfur, so they drained it. But let's say that it had some sludge that was left in the bottom, and they drained it, and they got it down there, but they might have left some of that sludge in there. And then they filled it up with ultra-low sulfur diesel. Sludge tends to act a little bit like a sponge. So there was trace residuals of this higher sulfur diesel fuel left in there. In a 1,000-gallon tank, all you need is 15, 20 gallons of just leftover trace low-sulfur diesel in order to throw the whole thing out of compliance. Okay, so there's a lot of tanks that are out of compliance out there. Now, in and of itself, basically, who cares? Why are we even talking about this? And to a certain extent, contamination with high sulfur diesel, this is not a performance issue. It's not going to destroy equipment by and large. It's not going to, it's not going to cause engine problems. What this becomes is a compliance issue and a legal issue, because when they switched over to ultra-low sulfur diesel, the Department of Transportation, which are the people that tend to enforce this, they announced penalties. If you were a truck driver and you had your fuel tested and it was found to be out of compliance, then you were faced with penalties of $32,500 per tank per day. And they would backdate that, and they would assume that you had been using this fuel for, 21 days, 28 days. Naturally, when you're looking at six-figure fines, potentially, the industry said, whoa, that's a problem. The EPA kind of worked with them and allowed a slower implementation of the ultra-low sulfur diesel, but that implementation period, which was designed to try and get this higher sulfur fuel out of the system, that is over with. So this effect of possible contamination with high sulfur diesel, this is a legal liability issue that people who manage fuel have to be concerned with. Fourth effect, cold flow properties. Bell Performance is located in Florida. We do not tend to have cold flow problems down here, but we have a lot of people we deal with, a lot of customers, a lot of fleets up north. If you're up north in Michigan, Illinois, New York, anywhere, above the Mason-Dixon line, you know that diesel fuel has cold flow issues in the winter. Diesel fuel naturally contains what they call paraffin wax components. Those are normally dissolved and burned seamlessly as part of the fuel, but when the fuel starts cooling down, some of those start to drop out of solution. They form crystals in the fuel. Those crystals bump into each other. They get bigger. Over time, as the fuel continues to cool, more and more are coming out, and eventually what happens is that the fuel thickens, and you get enough of this wax in there that it will do what's in that picture. It plugs the filter, and when the fuel filter is plugged, the engine shuts down because there's no fuel flow anymore. Now, ultra-low sulfur diesel has issues with this because of the processing. When they removed sulfur, they also removed and destroyed some of the compounds like the aromatic compounds that in the old fuel, these molecules would act as dispersants, and they would keep if the wax crystals came out of solution, they would keep those wax crystals apart. Now they're not in there anymore. There's nothing to keep the fuel from gelling at a higher temperature, and that is exactly what happens. So what problems does this cause? Well, the fuel gels at a higher temperature, which means you have a greater, well, not a greater amount, but you have more gelling problems in a given winter period. And so you get increased filter blocking, you get operability issues, and if you are a business and you're running trucks out there, then anytime you have the potential for operability issues, you have the potential for lost business and big-time headaches. So big difference between how ultra-low sulfur diesel behaves in the field and the old fuels is that ultra-low sulfur diesel is much more sensitive to cold weather problems than before. The fifth and last one that we're going to talk about, lack of resistance to microbes. And this is probably the biggest one. This is the one that has the potential to affect the most number of people in the most serious way. Now, regardless of whatever kind of fuel you're putting in a storage tank, microbial presence in those storage tanks is a universal problem faced by every person that has a fuel tank, everyone. That's because microbes are ubiquitous in the environment around us. We already know that. They get into the tank by any number of ways. It's not like somebody's taking a petri dish and dumping the contents into a tank. No, I mean, all that needs to happen is you get dust that comes in. You can have hundreds of millions of microbes on one single particle of dust. Water gets in, whether it's by a tank leak or by just water vapor on the air. If you get a fuel drop, somebody drops some fuel, they got microbes in their tank. It spreads very easily from tank to tank. And so they get into the tank, and what they're looking for is some kind of water layer. Anytime you have water in the tank, you have a layer of water on the bottom, you have fuel on top, and those microbes are going to go down and they're going to settle into the interface, where the two layers meet. And they're going to draw what they need from both sides, and they're going to grow, and they're going to thrive, and they're going to multiply, and they're going to produce biomass and all sorts of stuff that's going to cause problems. Now, we mention water because, as this point says, microbial growth, anyone that has a free water layer in their fuel storage tank has the very real possibility of having a microbial growth problem. It is not a matter of if, it is a matter of when. I mean, seriously, that it's not a matter of if, it's a matter of when for those types of situations. But most people don't seek to have a water layer. I mean, how does water build up in a tank? Well, again, it can happen just by natural processes. I mean, even just simple condensation. Fuel, you get a 7-degree temperature difference between daytime, and then when it cools down, temperature drops. Any water vapor that's in the tank from air that has exchanged through airflow, that's going to condense on the sides of the tank. It's going to roll down to the bottom because water is heavier than fuel, and there's going to build up a water layer over time. And this is probably elementary stuff to those of you out there who have dealt with tanks in any significant capacity. I mean, that's just the way it is. But even beyond condensation, you could have, when you get a fuel drop, somebody could transfer water during the fuel drop. You could have, if you've seen the gas stations where they have the underground tanks and they have they have the openings and they have spill buckets designed to catch water, and those can have a couple, those can hold 2, 3, 4, 5 gallons of water. Somebody goes to do a fuel drop or something, they're not paying attention. Some of that water goes into the tank. There are enough ways for water to get into tanks that it's virtually inevitable that a storage tank is going to build up water. So microbial problems are a potentially big issue. What problems do they cause? Now, this is kind of the so what part. What problems do they cause? Well, first thing is that fuel microbes are associated with filter plugging, and they're very easy to spread to other areas. They produce biomass, they produce slime because of the natural processes that they're the byproducts of their natural processes. And the biomass, it clings to the sides of the tank, it gets into the filters, it plugs them, and that's why if you manage any amount of tanks, you tend to know how often you have to change those tank filters. And when you start to notice that frequency is shortening or changing suddenly, that is a surefire sign that something's going on in that tank that you need to check out. And just like infections in the human body, infections in fuel tanks can be very easily spread anywhere that fuel goes. I mean, it's just the way it is. Second problem is that microbes tend to destroy fuel stability, And if you add microbes to fuels that have cracked stocks, you get a double effect. Microbes, when they grow, they produce acids, they produce biological byproducts, and those will attack the fuel and they will break down the fuel quality. What problems does this cause? Well, you get the exact same problems as you do when we were talking about fuel instability. All of those, deposits in the engine, black smoke and emissions, rough, inefficient engine operation, that all of the problems that are associated with unstable fuel, they're going to be associated here as well. Now, you remember when we were talking about fuel users and we had the generator, we had the black smoke picture, and I talked about system operation and the possibility of systems not operating the way that they should. This is where we circle back and talk about that a little more. Consider places that store fuel for emergency use, like hospitals, like businesses like telecommunications businesses, public utilities. Places that have to keep going and cannot have their systems shut down. So they have backup systems with stored fuel. Now, the nature of stored fuel, or what we call emergency use fuel, is that those tend not to be checked very often. I mean, the fuel is there because they might need it at some point, but they don't know when they're going to need it. They just know that when they need it, it has to do what they needed to do. It absolutely must. So there's a very, very high value placed on that stored fuel performing properly when it's called on to do so. Now, as we have implied, the nature of emergency means they don't know when that fuel is going to be needed. And so because of human nature, unless there is a rule in place that says you must check your tank every month, you must check the tank, test the fuel, do whatever, X number of times within a year. Unless there's something directing people specifically to do it, people tend to leave that alone because it's out of sight, it's out of mind. And so what you get is you get problems that arise when emergencies happen and the fuel in that tank hasn't been checked. You get a higher chance of what we'll call critical system failures. What comes to mind is, Hurricane Katrina back in 2004 or 2005, and then the most recent Superstorm Sandy that pummeled, the Northeast. In both cases, there were emergency systems that had significant amounts of fuel that had not been checked because they didn't have any reason to check them. It was out of sight, out of mind. They just assumed that it was going to do what they needed to do. And there were publicized problems. There was a hospital that did not have its generators, its essential backup generators work properly, and I believe there were some human casualties involved with that. So, again, this type of stuff, it's out of emergency use fuels, out of sight, out of mind. You don't know when you're going to use it. And if there's a problem, unless you're checking it, you won't know that it's not going to do what you need it to do until it is too late. And the biggest culprit in those situations is microbial buildup in those storage tanks. Now, microbes cause instability. They cause filter plugging. What they also cause is what they call microbe-related corrosion. Within the industry, it's abbreviated as MIC, microbially induced corrosion. We mentioned earlier that microbes, as a natural part of their biological processes, they produce acidic compounds. And those acidic compounds do exactly what you think they do. They attack storage tank surfaces, and they start to corrode surfaces and components inside of that tank. There are cases where some types of bacteria have been known to eat through a 5 millimeter thickness of 316 grade steel in 1 to 2 months. Now that is an extreme case, but it is a documented case. And it basically serves to illustrate what can happen, the kind of serious damage that these microbes can cause. And, this kind of damage is, it's expensive. Anyone who deals with tanks knows that even if you have to replace parts inside of them, it's at least hundreds, if not thousands of dollars. And it's not something that is a budgeted, expected expense either. Now, how did the changes to ultra-low sulfur diesel, how did it lead to microbe problems? Okay. Well, there are two inherent qualities of ultra-low sulfur diesel that have caused it to be more susceptible to these issues. First one is that it is more what we call hygroscopic, means that it tracks water sulfur was a natural biocide that tended to inhibit microbial growth. Microbes do not like being around high sulfur content. That is why it used to be when you had high sulfur and low sulfur diesel fuel, the conventional wisdom was that as long as you kept the water under control, you would not have to worry about microbial growth in those fuels. Now you take the sulfur out, and there is virtually nothing in that fuel that's going to keep these microbes from growing and thriving in them. And so that is why if you have ultra-low sulfur diesel in a stored fuel tank, microbial problems have potential to be huge problem. Okay, now let's cycle back for a moment back to remember we talked about those old storage tanks, right? The old storage tanks that have had fuel in them for years and years. Go back to the last time we had a major hurricane, really active hurricane season. That was around 2003, 2004, 2005. When hurricanes are coming, people tend to, checking the fuel, the backup fuel in the tanks tends to be more important when more urgent than when imminent danger is not imminent. So a lot of those tanks, they had fuel added to them back then. And because it was 2004, 2005, that was before the changeover to ultra-low sulfur diesel. So what you've had is you haven't had any active hurricane season since ultra-low sulfur diesel was added to those tanks. And what that means in practice is that a lot of those tanks have not had the attention paid to them that they need to. And, if we suddenly have, let's say next year the hurricane season is a little more active than it has been, a lot of those people are going to go to use those tanks, and there's, unfortunately, there's going to be some very serious issues because they haven't been checking them. Now, the smart people, the smart businesses, and the smart entities, they are going to be proactive, and they're going to check out their tanks. They're going to make sure that the fuel is up to standard if they're not already directed to. Okay, so we've got a few minutes left. So what we want to do in this last part of the webinar is, we spend a lot of time talking about the problems and why, and all the little details about what exactly led up to those issues and the problems that those cause. So what we want to wrap up with is we want to talk about action. Okay, what do you do about these? And these are the kinds of solutions that the industry has figured out for these problems. So we're going to spend a few minutes, just go over these briefly, and then we'll wrap up. We'll take some questions at the end, and we'll be out of here. So first problem, remember, talked about fuel instability. The problem was, heavy fuel components, deposits and sludge in storage tanks and in engines, things like that. The cause being, refinery cracking methods, and also the actions of microbes in the fuel. Anybody who uses stored diesel is affected potentially by this issue. The recommended measures is that you have to treat the fuel when it is fresh. You have to treat the fuel with a stability treatment. Now, there are a number of options out there in order that are effective. Some are better than others. If you're looking for a stability treatment, what you need is you actually need it to be a package of things. It's not one thing. It's actually 3 or 4 main things. It has to have an antioxidant in it, which stops the oxidation reactions. It stops those chain reactions. It has to have a dispersant in it that will keep sludge particles away, dispersed in the fuel and keep them from agglomerating and polymerizing. And it also helps if it has something to stop, something what they call a metal deactivator, which is there are certain kinds of metals like copper that tend to be great catalysts for making fuel go bad. So a metal deactivator will neutralize the effect that that metallic exposure has. And lastly, all of the good stability treatments out there in the marketplace are actually designed to be pretty cost effective by having what we call low treat rates, at least 1 to 2,000, if not 1 to 3 or more. So if you happen to have something that claims to be a stabilizer, and it wants you to put 1 to 1,000, you probably do not have one of the better ones. And like we said, absolute number one thing you have to do is add it at the beginning before the reactions are starting to take place, because they will stop reactions, but they will not reverse reactions. Second problem we talked about, cold flow handling problems, again, caused by fuel gelling, paraffin wax dropping out because of the fuel getting cold. Anyone in a cold weather climate any diesel user has the potential to be affected by this. Recommended measure, similar to stabilizers. The only thing you can do is treat the fuel with what they call a cold flow treatment, and you have to do it before the fuel gets cold. Now, fuel management professionals will know that their fuel tends to cloud up at a certain temperature. It's recommended to add a cold flow treatment before that happens. They work by basically keeping the wax crystals small and away from each other, and that keeps the fuel from gelling. Addition to the fuel above the cloud point, which for most fuels is between 20 and 30 degrees Fahrenheit, that is basically how you do it. Last thing to say about this, we've mentioned about engine designs. Common rail diesel engines are pretty much the standard now. And common rail diesel engines have smaller filters. They have, they're higher pieces of technology, and they spec smaller fuel filters because they want to keep absolutely everything out of that engine. Now, while that's good for the engine, unfortunately for fuel gelling, that actually exacerbates the problem because the fuel filters plug more easily with smaller amounts of wax. And so the recommendations for treatment of fuel for fuel gelling are that if you thought that you didn't have to worry about it until the temperature got to 30 degrees, or well, let's say 25 degrees, now they're saying add 10 degrees to that and start worrying about it when it's 35 degrees. So that's an area where the change in engine technology is forcing human behavior to adapt to it if you don't want to have problems. Excessive sulfur level in diesel, again, we talked about that this was basically not a performance issue, it was a liability issue. And so the only way that you can get around that is basically to dilute the fuel. Means use the fuel if you can, but then keep adding more ultra-low sulfur diesel until that fuel sulfur level is diluted enough. Now, the reason we bring this up is because we have been asked, there are places like fuel polishers. There's a lot of fuel polishers out there, and some of them, in the effort to differentiate themselves from the competition, they make certain claims like, if you have fuel that has too high of sulfur content, well, we can polish that sulfur out of that fuel. Well, it does not work that way. There's nothing that a fuel polisher can do through a polishing mechanism or a mechanical process that will reduce sulfur level if it's too high. The only thing you can really do is dilute the fuel or, unfortunately, get rid of it. That's really the only thing that you can do. Storage tank corrosion, caused by water absorption and by microbial, the acidic byproducts of microbes in the fuel. The recommended solutions for this are to try and keep microbes and water out of that tank. That means you have to check the tank on at least a monthly basis. You want to consider using biocides in order to kill any microbes that may get in there. And there's also anti-corrosive, what they call anti-corrosion tank treatments that you can also use that will protect the tank surfaces. Sludge buildup in storage tanks, again, related to the whole issue of fuel instability. So the way to solve sludge buildup is you use a stabilizer to keep that sludge from forming, and you use antimicrobial biocides to keep microbes from destroying that fuel quality and accelerating the formation of the sludge in those tanks. And then I think the last big one, it was the last one that we talked about earlier, the whole issue of fuel and tank microbes in there. They call the myriad of problems. Anytime you have water in the tank, you get the possibility of them establishing themselves in the tank. And anyone who stores fuel, especially if you don't monitor the fuel regularly, you have the very real possibility of being affected by the problems that are associated with them. Now, the recommended measures for dealing with fuel and tank microbes typically get divided into two main categories. You have what they call housekeeping measures, and then measures designed to deal with an existing problem. Housekeeping measures are things that you do to prevent them from growing in the tank. And the biggest one there is just staying on top of the free water buildup as regularly as possible. But if you have microbes that do establish themselves in there, then housekeeping measures are not going to do anything for those. The only thing that you can do then is treat the fuel in the tank with a biocide. That biocides are the only thing that will kill microbes. You can get rid of the water. You can even use things that claim to, absorb water or control water. But if you have living microbes in that tank, those water controllers will not get rid of those problems. That is one of the biggest misconceptions in the industry, is that all you have to do is control the water and you'll get rid of the microbes. That is absolutely not true. Biocides, if you have an existing microbe problem, you have to use a biocide. Now, there are a lot of different biocides out there, and the reason we're finishing up with this is because this is something that something that's very important for people who store and process and use fuel, but it's something that a lot of them don't know a whole lot about. There's a lot of things. There's different chemistry options. There are, like I said earlier, there's things that claim to control microbes by controlling water that aren't really biocides. And unless you know specific things, how are you to know which one is the right one to choose? Well, there are certain hallmarks or characteristics that you want to look for if you're looking to choose a good biocide to solve your problem. It should incorporate the following characteristics. Okay, what do we call broad spectrum? That basically means it has the ability to kill as many of the main kinds of microbes, and that's bacteria and fungus and mold, that are typically found in a tank. It should kill the whole spectrum of them. Fast acting. Typically, if your biocide is properly applied and kills everything within an hour to 1 to 2 hours, then that's generally what you're looking for. There are ones that are faster than that. If it's more than 2 hours, you may want to consider looking at something else. Long-lasting kill, that is the big one. You want the biocide to keep working and be effective for as long a period of time as possible. Now, one thing to remember with this, when we're talking about what they call kill length, biocides are not a one treatment and last forever type of thing. The most that you will generally expect reasonably to get out of a biocide treatment is about 4 to 5 weeks. But a lot of them are shorter than that. Some of them only last 1 week, maybe 2. So if you can have one that lasts 4 or 5, maybe 6 weeks, you're pretty much getting the better ones, best ones in the industry. But it's also something where if you want to keep microbial problems out of the tank, you need to keep checking, and you need to plan to reapply maintenance doses of biocides, ideally once a quarter. But twice a year would be good. Quarterly would be better. This is another important one, what they call dual phase effectiveness. You're going to have water and you're going to have fuel. Now, they do recommend if you've got an infected tank that you remove water, as much of that as possible. But if there's any water that's left, you want that biocide to work both in the fuel, and then you're going to want it to migrate down, and you're going to want it to what they call partition into the water or move into the water. And when it does this, then it will move across that interface, which, if you remember, that's where we said a lot of the microbes do their best activity. So that biocide moves across the interface, and it does the best job of killing. The one thing we haven't mentioned many specific products here, but the big one with respect to dual phase effectiveness and not being effective is BioBor. It's the most well-known one in the industry because it's been around the longest time, but it actually is the poorest effectiveness for a biocide, and if it comes in contact with water, it actually crystallizes and stops working. Last one, registration with the EPA. This is a big one, and this is a key way to know if you've got a good biocide or not. An actual legitimate biocide, not some potion some joker whipped up in his garage and then is trying to sell on the street, but an actual good biocide with an effective chemistry, those are required to be registered with the EPA. And they're required to have their registration numbers printed on the labels. So if you want to know if your biocide or if you've got something that's claiming to be a biocide, if you want to know if it's legit, look for the registration numbers. And we say numbers because there are two of them. If it has them and then they're easy to find, you're good to go. If it doesn't, then maybe need to reconsider the one that you're using. And the last thing, sometimes tanks will get, remember we said that microbes produce biomass. Sometimes what happens is that biomass, which is a sticky, kind of nasty matrix of basically biological material, that stuff will cling and settle on surfaces, and microbes will actually hide behind that. And you put a biocide into the tank, those microbes are shielded from the biocide, and then when the biocide's been used up, they come back out to play and they reinfect the tank. If you know that you've got biomass in that tank, then there are dispersants that you may want to pair with that biocide that will bust up that, essentially poke holes in that shield and make the biocide that you're using even more effective. And the last thing that we're going to mention, proper application for biocides is absolutely key. You want to remove as much of the water as possible to start with. You add the biocide, and then you need to circulate the fuel for a given amount of time to allow time for that biocide in the fuel to contact the microbes and kill them. Then when you're done, you need to wait about 8 hours to allow for the dead microbial bodies essentially to settle down to the bottom of the tank, because biocides kill them, but they don't make them disappear. Now they're all dead, and if they run through the filter, they're going to plug that filter, which isn't a bad thing. It's just the way it is. So wait 8 hours before using the fuel, and keep extra filters on hand, most definitely, for keeping around as those bodies get caught by the filters, basically. If you have not been to the Bell Performance website, we have a blog where we write regularly on things like this, and we have other more detailed recommendations available on the Bell Performance blog, which is at our website. All right, so we've gone a little bit over time, but that's okay. Like I was saying, we have more information available at the Bell website. We actually have two website URLs, bellperformance.com, and then also one called wefixfuel.com. And what we've tried to do is put a lot of useful information on those. There are downloadable resources. There are blog articles written for both businesses and consumers, targeting, explaining some of the topics that both sides happen to be interested in. So if you want more information on any of this, that is a great place to go and start. And we also had, like I said, there's downloadable resources on lots of different kinds of topics available at the Bell website. Just go to bellperformance.com and click on the Resources tab, and you'll see something like this. All right, so last but not least, any questions that we might have? We had some questions that were submitted earlier. If you think of a question later, and you can't think of it now, but it occurs to you later, everyone should have an email from me that had the registration information and the phone number. Just send me an email with your question. I will be very, very happy to answer, as well as I can. I think what we'll do in the last couple minutes here is there is one question that several people asked before the webinar, and it had to do with something that I mentioned in passing, which is the thing about fuel polishers. Remember, I was talking about sulfur content, and there are a lot of fuel polishers out there, and there's some confusion among people who have stored fuel because they're confused a little bit about what fuel polishers claim to be able to do versus what makes a good one versus a bad one. Now, we could do a whole nother webinar on that topic, but we don't have time to do that. So in a nutshell, basically, fuel polishers, the best fuel polisher, if you find that if you have a tank that's got a lot of stuff in it that you need to get out, a fuel polisher is a great resource to call to do that. But the best fuel polishers will actually use what they call a hybrid approach. They will have a mechanical process where they use high quality filtration down to typically down to 1 micron to get the water and the sludge and the particulate out of that fuel. But they also need to pair that with the best chemicals. Remember, we talked about the fuel stabilizers and the biocides, because polishing and mechanical processes can clean the fuel up, but it will not prevent problems from coming back. And you want your fuel to be clean, but you also want it to stay that way. So the best reputable fuel polishers will use both approaches. They will incorporate good, effective chemical treatments in with their high-quality filtering processes. All right, so I think that is about it for this encore presentation of the Bell Performance webinar. Again, if you have any questions, email me at ebjornstad@bellperformance.net. Everyone should be getting an email in the next couple of days that will have a link to download the recording of this. And also there may be a little evaluation thing. If you would just take a minute and just answer a couple of questions, we want to make sure that the future webinars that we do are even better than this one. And so in order to do that, we need to know how we did. So I think that is it. And thank you very much for attending. We will probably be offering another webinar probably in the first quarter, so we'll send out the information about that. But in the meantime, we hope everybody has a fantastic day, and thank you very much for coming. All right. And we'll talk to you later. Bye-bye.